Welcome back to Vox AI News. I'm your host, Alice, and as always, I'm joined by my wonderful co-host, John. How are you doing today, John?
Hey, Alice. I'm doing great. Thanks. Excited to dive into today's topic. We have something really fascinating lined up, don't we?
Absolutely. Today, we're discussing a groundbreaking development in neural networks, the Sparsely-Gated Mixture-of-Experts layer, or MoE for short. This innovation promises to significantly enhance the capacity of neural networks without a proportional increase in computational costs.
That's right. The concept of conditional computation is at the heart of this development. Can you explain what conditional computation means, Alice?
Sure. Conditional computation refers to activating only certain parts of a neural network for a specific input example, rather than using the entire network. This approach allows for a dramatic increase in model capacity while keeping computational costs in check.
Interesting. So how does the sparsely-gated mixture-of-experts layer fit into this concept?
The MoE layer consists of multiple expert networks, each capable of processing input data. A gating network determines which experts to activate for each input, allowing for a sparse combination of these experts to be used at any time.
That sounds powerful. How does this approach actually improve the model's capacity?
By using a large number of experts, potentially thousands, only a few of which are activated for each input, the MoE can effectively manage a much larger number of parameters. This results in substantial improvements in performance on tasks like language modeling and machine translation.
Speaking of performance, what kind of improvements have been observed with the MoE layer?
In experiments, models using the MoE layer have achieved over 1,000x improvements in model capacity with only minor losses in computational efficiency. This is a game changer for deep learning applications.
That's impressive. Can you give us some context on how this compares to traditional neural networks?
Certainly. Traditional neural networks activate all their parameters for every input, which leads to a quadratic increase in computational costs as the model size grows. In contrast, the MoE layer selectively activates parts of the network, allowing for a more efficient use of resources.
So, what challenges did the researchers face when implementing this approach?
Great question. Some challenges included the inefficiency of modern GPUs with branching, the need for large batch sizes for performance, and network bandwidth limitations. They also had to ensure that the gating network effectively balanced the load among experts.
How did they address these challenges?
The researchers tackled these issues through a combination of algorithmic and engineering solutions. They implemented a gating network that uses a noisy top K selection strategy to maintain sparsity and balance expert utilization.
That's fascinating. Can you explain how the gating network functions in more detail?
Certainly. The gating network computes a score for each expert based on the input and selects the top K experts to activate. This selection process is influenced by added noise, which helps with load balancing and prevents certain experts from becoming overly favored.
What are the implications of using a sparsely gated system like this in real-world applications?
The implications are significant. For instance, in natural language processing tasks, the MoE layer allows models to better understand context and nuances in language, leading to improved translation and language generation capabilities.
That's exciting. Can you share some specific results from their experiments?
Sure. In a benchmark using a 1 billion word dataset, models with MoE layers achieved a 24% lower perplexity compared to traditional models with similar computational budgets. This indicates a much better performance in predicting language.
What about larger datasets? Did the MoE models perform well there too?
Yes. When tested on a 100 billion word dataset, the MoE models showed even greater improvements, with significant drops in perplexity as the number of experts increased, demonstrating that larger datasets benefit from higher model capacity.
And how did they perform in machine translation tasks?
In machine translation, the MoE models outperformed existing models, achieving higher BLEU scores, which measure translation quality. This shows that the MoE layer is not just a theoretical improvement, but has practical applications in real-world tasks.
It sounds like the MoE layer could revolutionize how we approach deep learning. Are there any limitations to this approach?
One limitation is that as the number of experts increases, there can be diminishing returns in performance. Additionally, managing the balance of load among experts is crucial to ensure that all experts are utilized effectively.
What future developments do you foresee in this area?
I believe we will see more implementations of conditional computation across various domains beyond just text, like image processing and audio analysis. As hardware continues to improve, the potential for larger models will only grow.
That's a great perspective. Before we wrap up, what's the key takeaway from today's discussion?
The key takeaway is that the sparsely-gated mixture-of-experts layer represents a significant advancement in neural network design, enabling much larger models to be trained efficiently, which could lead to breakthroughs in AI applications.
Well said, Alice. Thank you for such an informative conversation today. It's always a pleasure to explore these topics with you.
Thank you, John, and thank you to our listeners for tuning in. We hope you found this episode enlightening. Stay curious and stay informed.
We'll catch you on the next episode of Vox AI News.